Welcome back to The Explainer. Today, we're stripping down the engine of modern distributed systems to look at a real game changer. I'm talking about one of the most powerful performance multipliers in software engineering, the mechanics of system caching. If you're building or scaling systems right now, understanding how to strategically hold and serve your data is absolutely non-negotiable. So we're going to break down exactly how to optimize the flow of data, from the edge all the way down to the database. Okay, let's dive into this. It's literally the universal question that keeps engineers up at 2 a.m. Why is your application so slow? You know the drill. You've optimized your code, you've spun up more instances, but the bottleneck, it almost always points right back to a sluggish database, trying to read from a physical disk. Network calls are slow, and disk I/O is even slower. Every single time a user requests data, sending them all the way back to your primary database is just an incredibly expensive trip.
To fix this, we really need to establish our baseline metrics first. System performance basically comes down to a fundamental tug of war. You have latency, which is the time it takes for one single request to complete, say 50 milliseconds for an API call. And then you have throughput, which is the sheer volume of requests processed per second, like 10,000 RPS. Usually, you kind of have to trade one for the other. But caching is the ultimate latency hack. It lets us drastically drop the time per request while simultaneously freeing up database resources to handle way higher throughput.
Section 1. The need for speed. So how exactly do we solve this latency issue? Well, think of your database like a fast food kitchen during the absolute peak of the lunch rush. It's incredibly powerful, capable of making literally any complex order on the menu. But under heavy load, it gets totally bogged down. If every single customer asks the chef to cook a burger from scratch, the entire line just halts. Caching is like putting a tray of freshly made, ready-to-grab burgers right at the front counter. It introduces a super fast in-memory storage layer, using RAM instead of spinning disks, so that those most frequent requests never even reach the kitchen. Section 2. Real-world caching examples. To ground this theory in some tangible architecture, we have to recognize that mastering this isn't just some theoretical exercise. It has massive business implications. Take Pinterest, for example. By implementing smart caching strategies, they achieved a staggering 70% cost reduction in their feature serving. 70%. When you're operating at scale, reducing the load on your primary data stores by serving data from memory doesn't just make the app feel snappier to the user, it literally saves millions of dollars in infrastructure costs. And if we look at Discord, their scale is almost impossible to comprehend. They're handling 50 million feature lookups every single second. To actually pull that off, they rely heavily on distributed key-value stores. A standard database simply cannot serve 50 million complex queries a second without bankrupting the company. But a well-architected distributed cache, it handles that sub-millisecond latency with total ease. But here's the thing. Caching doesn't just happen in one place. It lives at multiple layers of your architecture. Out at the edge, you have browser caching and content delivery networks, or CDNs, which push static assets geographically close to the user. Deeper in, you've got your application-level in-memory caches. Then you have your distributed caches in the backend, like Redis or Memcached, acting as this massive shared memory pool across your servers. And finally, even your database has its own internal query cache. Every single layer is designed to intercept a request as early as possible.
Section 3. Caching strategies and trade-offs. Okay, we're at the real climax of our discussion here, because deciding how to cache is a constant tug of war between keeping data perfectly consistent and keeping latency low. Let's slow down for a second and walk through the most common strategy, the cache aside, or lazy loading pattern. Step 1, the application checks the cache for a key. Step 2, if it's a miss, it queries the primary database. Step 3, it stores that new result in the cache with a time-to-live expiration. And Step 4, it returns the result to the caller. It's fantastic for read-heavy workloads purely because the cache only stores what's actually requested. But what about when your data actually changes? Well, in the write-through pattern, the application writes new data, which instantly updates the cache. Then the database is synchronously updated, and only after both are complete is success acknowledged. This pattern is brilliant because it keeps your cache data perfectly fresh. However, that safety comes at a cost. Because you have to write to two places synchronously, your write operations are definitely going to be slightly slower. Now, what's really interesting about this slide is comparing the absolute safety of synchronous updates against the sheer speed of asynchronous flushes. If write-through prioritizes safety, its aggressive cousin, the write-behind pattern, prioritizes pure speed. The app writes to the cache and gets an immediate success response, while the cache asynchronously flushes that data over to the database later on. It's incredibly fast. But if the cache crashes before that flush happens, you permanently lose that data. It's the classic availability versus consistency trade-off.
Then you have the predictive power of refresh-ahead caching. This is where the cache is configured to automatically refresh any recently accessed entry just before its expiration. You're essentially trying to predict the future. If you guess right, you completely eliminate read latency because the data is always hot and ready. But if your system guesses wrong and refreshes data that literally no one ever asks for, you introduce a dangerous performance bottleneck, wasting valuable CPU and database resources on phantom requests.
Section 4, Eviction and Cache Invalidation. So what happens when the cache inevitably gets full or the data becomes stale? As the legendary quote by Phil Carlton goes, there are only two hard things in computer science: cache invalidation and naming things. And this brilliantly illustrates the central conflict here. Figuring out exactly when a cached value is no longer accurate and ensuring no user receives stale data without entirely tanking your system's performance is a famously difficult engineering challenge.
Because RAM is notoriously expensive and limited, your cache will fill up. It's a guarantee. When it does, engineers use an arsenal of eviction policies to clean out the memory. You've got LRU, which kicks out the least recently used items. This is your go-to, most common general purpose policy. You've got LFU, least frequently used, which is great for really stable access patterns. You have simple, FIFO, first in, first out. And of course, TTL, time to live, which just automatically expires items after a fixed duration. Choosing the right policy dictates your entire cache hit rate.
Section 5, Production Bottlenecks and Failures. Which brings us to the cautionary tale of what actually breaks when caching is implemented poorly. What really happens when caching goes horribly wrong under massive scale? Well, caching hides a lot of underlying system weaknesses. If your database is fundamentally weak, a high cache hit rate will mask that reality, right up until something disrupts the cache, immediately revealing the fatal flaws of your distributed system under load.
Let's look at the gritty reality of these edge cases. First up, cache stampedes. This happens when a highly requested cache key expires and suddenly thousands of concurrent requests all miss the cache and hit the database at the exact same millisecond. It can bring the whole system down. Then you have Redis hotkeys, where a single, super popular piece of data overwhelms the specific shard holding it. You also really have to worry about network amplification and improper cache sizing, where over-caching sensitive data or under-caching vital data leads to either correctness issues or totally exploded infrastructure costs.
We've seen how caching is an incredibly potent tool, but at the end of the day, it's fundamentally a game of trade-offs between speed, cost, and data freshness. So I want to leave you with this provocative thought to analyze within your own applications. Is your current architecture sacrificing too much consistency just to stay available? Take a hard look at your read and write paths and ask yourself, is your caching strategy actually serving your users, or is it just hiding your bottlenecks?